We are happy to have with us today Zuzana Patáková. Zuzana is a professor at Charles University in Prague. I mispronounced something, I assume. That was why you looked at me weird.
No.
Okay. Zuzana has impressive works in a lot of different parts of discrete and computational geometry. But I believe in recent years she has been focusing mostly on more topological topics, but she's welcome to yell at me if I'm wrong, or even just for whatever reason. You might have noticed that this semester we have a theme. Most talks somehow were related to Tversberg's theorem, Helly's theorem, something like that. So Zuzana is continuing this sequence. And I will be quiet, and to you, Zuzana.
Thank you very much. This was a beautiful introduction. I think I never had such a nice one. So as Adam already said, this talk is from discrete geometry. And here we focus on extended results from convex geometry by the standard convex setting. So some topology is unfortunately needed, but I will try to avoid it as much as possible so that you can enjoy it as much as possible. Okay, so let me start with three fundamental results from convex geometry. So this is the setting. We have n convex sets in, say, in a plane or in general in d dimensions. And if we know that every three sets intersect, then all sets intersect. This is a result of Helly. In higher dimensions, we just simply replace 3 by d plus 1. Okay, and here, the d, it does not depend on the size of the family of n when I go to higher dimension. And in some sense, this is kind of, here we have a local property, only 3 sets intersect, and I have a global conclusion, all sets intersect. Yeah. However, in practice, convex sets often comes from some measurements. And here we can expect to have some outliers, which corresponds to error in the measurements. Yeah. So now question is, for example, what can we say about intersection patterns of our family if we know that only 88% of triples of the sets in a plane, or like convex sets in a plane, intersect. So here was this small example here. Not all sets intersect, but just like a huge number of triples. So can we conclude that, for example, can we conclude that 88% of all sets intersect? Unfortunately, no, but we still can guarantee something, and we can say that there is a point common to at least half of the sets. So this phenomenon, in fact, holds much more generally, and in the sense that if I have a positive fraction of intersecting triples, then I conclude there is a point common to positive fraction of all sets. And this was shown by Kachalski and Liu, and it also extends to higher dimensions. Just replace 3 by d plus 1. And last result I want to mention is, or it gives a simple and sufficient condition on a finite family of convex sets to have a hitting set of a constant size. So Alon and Gleitman, they show that if among any p sets some q intersect, then the entire family can be pierced by a finite number of points. And this is called a PQ theorem, and it's related to the results above, and it's like also very nice, very beautiful result. Okay. Questions? So, and now we will discuss what happens if the sets are not convex. Yeah? But I want to first formalize what we said on the previous slide, and we will be mostly interested in what was in the middle, and this is called fractional Helly theorem or property. So I will talk about fractional Helly property of some order D, and this is that my family satisfies it if for every alpha there is a beta with the following property. If I have a subfamily of my given family of a given size n, and if I know that at least alpha fraction of all d+1 tuples intersect, then I know there is a point contained in at least like some beta n members of the family G. So this is a crucial definition for this talk, so read it carefully or ask if something is not clear here. And I have here 3 very different type of examples which enjoy fractional Helly property. First one is purely combinatorial, and it was given by Jirka Matoušek, and it says that basically any set system with bounded VC dimension, it has like fractional Helly property of bounded order. This result it's not difficult. It's very useful, but it's not difficult. It's not hard. It's just about one need to unwrap the definitions very well. And it's combinatorial. There is no geometry inside. Compared to that, the second family or second example I have, convex lattice sets, this is geometrical one. Yeah. So what is this? We have what is a convex lattice set? We simply take a convex sets and we intersect it with a grid, integer grid. And what we get, this is what we call convex lattice sets. Yeah. So this such sets were studied with relation with optimization like 50 or maybe 70 or maybe even more years ago. And here the geometry is used. And what is surprising here is that if we want Helly number, if we are interested when in the case when alpha is 1, so it means if all d+1 tuples intersect, then I would like to conclude that all sets intersect. So if alpha is 1 and beta is 1, this reduces to Helly number. And Helly number would be like this, what I call here order. Yeah, maybe here is a slight shift by 1, but this is not that important. What I want to say that if I would like this, like if I need to check all tuples and guarantee that all sets intersect, then for this Helly, it's not enough to have d+1. I need to have an exponential number. I need to have 2 to d. Yeah, so what I'm saying that for this family, the Helly number is 2 to d, it's exponential in the dimension, but the fractional Helly number is d+1. Yeah, so there is this big gap, and the gap is necessary for the Helly. The Helly cannot be smaller. Okay. And last example I have here is about good covers, so it's topological one. It says what is a good cover? It's a family of open sets such that every non-empty intersection is contractible, meaning can be shrink just to a point. So, for example, clearly convex sets, they form, or open sets, they form a good cover because intersection of convex sets is convex, and convex means that it can be like to a point. Okay. And the proofs I know for this are like kind of heavy. Like it's either it uses some exterior algebraic shifting, or either algebraic shifting or some spectral sequence arguments. So like proving this, it's not, although it sounds very simple, the proofs I know are not very simple. And this will be the case we will be focused on. Like we want to ask, or the question is under which topological conditions we can guarantee we have a fractional Helly property. Okay. So in order to state the result, I need to work with some sets in RD, or work with some sets, and I need to measure the homological complexity of the set system. So what it is? So I take a positive integer k, I have a given family, and I consider some subfamily G of F. Now I take an intersection of all sets which are in this subfamily, so I'm here, and I compute first k reduced Betty numbers. Betty number, this is just, it counts basically number of independent holes I have. So I have these Betty numbers, and now I take a supremum over all these Betty numbers and over all subfamilies G. And this is what I call k-level homological complexity. So if this is too complicated, I have examples in a plane, and in plane is interesting enough. So I just tell you what it is in the plane, and if you don't like the general definition, it's good to have in mind just this. Yeah. So in a plane, if I have a family of sets, and if I know that any intersection is either path connected or empty, this corresponds to the case when the first level homological complexity is 0. Yeah. I just look at the intersection. If it's path connected or empty, I'm fine. So if I look at the second level, it means that any intersection must be simply connected or empty. So here, if I look, so I want to bound also the second Betty number, which corresponds to the fact here, if I mean it's trivial, it means there are no holes. Yeah. So first is about connecting components. Second, it's about holes. And if it's trivial, it means there are no holes in any intersection. And we will be interested in bounded homological complexity. So if this first level homological complexity is at most C, it translates in a plane to the fact that in any intersection of my subfamily has at most C+1 path connected components. If I want to bound also the second level, it means, of course, I need to have bound on the number of path connected components. It's at most C+1. But also I need to bound the more like one-dimensional holes, and it means I need to have, I can have at most C of them. Yeah, so here I have two path connected components and one hole. So here it could be that the homological complexity is at most 1 if it works for any intersection in my subfamily. Yeah. So for the talk, it will be like really important or not important, but enough to know what is the, if you reduce to a plane, what is the first homological complexity. If it's 0, it means intersections path connected or empty, at most C, bounded number of path connected components. Few examples, what are such families? So then we have a bounded homological complexity, which families, so for example, convex sets, they have it trivial because any intersection is path connected of convex sets is either empty or path connected. Yeah. The same holds for good covers. This was, we said that any intersection is either empty or contractible, which is basically this, that the homology is trivial. That the homological complexity is trivial. Spheres or pseudospheres, same. Yeah. Here the topological homological complexity is 1, I would say. Another example, algebraic varieties of bounded degree. So anything Adam plays with, basically. Yeah. Good. So now here is a picture. If I have a family in the dimensions, and I know that it has a bounded homological complexity up to the mid-level. So first, the half Betty numbers of all intersections are bounded by some constant, with some uniform constant. Then we have shown together with Xavier Guo, Pavel Paták, Martin Tancer, and Uli Wagner several years ago, that then we have a bounded Helly number. Yeah. So this is enough to have some bound on a Helly number. And what is here on the left top, not top, on the left bottom is another general result. And this is that we have, so it was shown by Alan Kalai, Matoshek, and Meshulam, which somehow said that in kind of general setting, when we have a fractional Helly theorem, we have also big epsilon and PQ theorem. I'm not very precise here, but it's kind of very general setting. So when we prove this result here, that constant homological complexity implies Helly, and you see how we draw it here. So at that time, Jirka Matošek asked us if we can prove also a fractional Helly from the same assumption. Yeah, so it's kind of, because it would mean it would have just nice consequences and so on, and like Helly, fractional Helly, it seems like they are quite related, although they are not that much. So it's really a basic or like a natural question. So we tried to prove it, but somehow we realized we cannot, that our method is not strong enough, or somehow it seems the theorems are kind of similar, but the proof methods, they differ a lot. Yeah, it's not true that if you have Helly, you can, by some standard arguments, show fractional Helly. No. So that was the situation. But then what happened is that Andreas Holmsen and then Guli, they showed that in very abstract setting, if we have a Radon theorem, we have a fractional Helly. So this was question of Gil-Kalai, if in some abstract spaces, we can this happen? And the answer, yes, it happens. And it's also quite known in discrete geometry that Radon implies Helly. Now, this was one proof of, I think almost of you saw a proof of Helly using Radon lemma. And this also generalized to abstract convexity spaces, that Radon implies Helly. So when I saw this, and also when you see this, I think it's quite natural to ask if we can prove that if we have a constant bound of the homological complexity, do we have a Radon? Yeah, because this Radon and Helly, they are much closer to each other. And if we would have this, then you see all these arrows, we would have also the other results. Yeah. And the answer is yes, we can prove that. Like this constant bound on homological complexity indeed implies bounded Radon, and then we would have all the other things. Yeah. So now I would like to explain a bit this Radon theorem.
Can I ask a question? It's a very silly question. So
sure.
This was asked by Irka. Is the paper dedicated to him?
I think already this paper was dedicated to him.
Okay.
Yeah, it took several years to get it published because somehow, the proofs are kind of complicated because it combines like topological methods and also Ramsey theory. And apparently it's quite difficult to find reviewers who knows both. Or maybe at least at that time, I don't know. Somehow maybe we were just unlucky. So it took us several years. But yes, this paper is dedicated to Jirka.
Very nice.
Very nice. Okay. So here I want to define what the Radon number is and what is this Radon. And let me do it in some higher generality because it's much nicer somehow. So for that, I need to define what is a closure operator. And this is just the operator working on, so I have some set X, and now I look at all subsets of X. So it goes from all subsets to X to all subset of X. And it must satisfy the following three conditions. So this is extensivity, that like simply the set is contained in its closure. Then we have monotonicity, that if A is under B, then closure A is contained in the closure of B. And here we have, I forgot how is it called, but like when you take a closure of a closure, you get a closure. Yeah, you get what you had already. And such sets are called closed. And for us, only two examples play a role. First one is standard convex hull. Yeah, you can check that convex hull satisfies all three conditions. Yeah, of course, any set is contained in its convex hull. Monotonicity also clear. If I take a convex hull of a convex set, I get the convex set. And second, maybe a bit more interesting example for us is a closure given by a family of subsets. Yeah, so I have some family of sets. And what is a closure of another set? It's simply an intersection of all sets from my family which contain my given set. And this is also a well-defined closure. It satisfies all these three conditions. And now I can define a Radon number of this closure operator. And this is simply the smallest R, such that if I take any set of cardinality R, I can split it into two parts, two disjoint parts, such that the corresponding closures will intersect. So this is what you know for convex hulls. And Radon theorem basically says that Radon number of convex sets is at most D plus 2. This is what you know when you want to prove Helly. And now the proof that Radon, that bounded homological complexity implies bounded Radon, it has two parts. First part is based on non-embeddability. A second is some kind of Ramsey type arguments. And here I would like to explain you the non-embeddability part because this is somehow kind of nice and simple. So for simplicity, I will just consider a closure operator in a plane. And I will also assume that closure of any 2 points is path connected. Yeah, so this is my setting. And I want to show that under these conditions, I have bounded Radon number, meaning the Radon number is at most 5. Yeah. So what do I need to show? So I have 5 points, and I want to partition them into 2 parts so that the corresponding closures will intersect. Yeah. So I have 5 points, this picture here. And what I know that for every 2 points, the closure of them is path connected. So what will I take? If it's path connected, it means I can draw a path between them. And the path is contained in the closure. Yeah. And I can do this for any 2 points here. So what I get is a drawing of K5. But we know that in a plane, when I have a drawing of K5, there must be 2 edges which intersect. Yeah, but these edges are contained in the corresponding closures because this is how we did it. Yeah, we take the path inside the closures. So since the path corresponds or the edges corresponds, it means also the closures must, if the edges intersect, it means also the closures must intersect. Yeah. So now you may protest a bit that I wanted to split 5 points and I split just 4 points. Well, but because of the monotonicity property, I can add the remaining point to 1 or to the second set. It doesn't matter. Yeah. So this shows that the Radon number is at most 5. Okay. And just let me briefly show you how to deduce, say, Helly number from that. That Helly number is 5. 4 for this case. So let's assume for simplicity we have just 5 sets. And let's assume they don't intersect for contradiction, but I assume every 4 of them intersect. Yeah, so and now if every 4 sets intersect, it means I can take a point inside. Yeah, so this is for set 1, 3, 4, 5. I will denote the point which is in the intersection P2 because like 2 was missing here. Yeah, so I get 5 since I have 5 sets, and all the time I think that 4 of them intersect, so I have 5 points witnessing that 4 of them intersect. So that's what I have here. And now look, for example, on the point P1 and P4. So this P1 is contained in F2, F3, F4, F5. This P4 is contained in F1, F2, F3, F5. And now if I take the closure operator given by the family, meaning that now I want to intersect all sets from my family containing my given set now will be P1 and P4. So the corresponding closure will be contained in what is common here. And this is F2, F3, and F5. Yeah, so you see that the closure is contained in, you know that the closure is contained in F2, F3, and F5. It might be smaller, but it's here. And the same for the second closure, this one. This is contained in what is in common, and this is F1, F2, and F4. Yeah. And since we have already seen that the closures intersect, so what is the point in common? So it's in this closure and also in that closure. So it's in all the sets, F1, F2, F3, F4, and F5. And this is a contradiction we had. Yeah, because I assume that no 5 points intersect. So this is how you derive Helly from that. Okay, so this was plain. This is the simple case. So what about higher dimensions? So first, let's see really what we have seen in the plane. So we use that K5 does not embed in the plane in its strong version, meaning that we needed that 2 independent edges don't intersect here. Yeah, I really needed that they are not adjacent to conclude that all 5. So for the Helly, for example, to conclude that all 5 sets don't intersect. So, and now if I would like to go to higher dimensions, so K5 embed in R3 and other things. So I would need another creature which does not embed if I wanna use this trick again. And fortunately, there is a result of Van Kampen and Flores, which says that D half skeleton of D plus 2-dimensional simplex does not embed into R2-2D. What is a K skeleton? I simply take all faces of dimension at most K. So for example, K5 is a 1 skeleton of 4-dimensional simplex. So, okay, so now if I want to continue, what was the trick? I had 5 points and I connected them by edges, if I could. So now I have the edges and I would like to continue. So I would like to fill in the triangles in case I can, in case there are no holes. So assume there are no holes, each triangle can be filled. So I can create like larger and larger creatures in this way until I hit this one, which is not embeddable, and this will be the stopping point for me. Yeah, this will give me that the Radon number is bounded. Okay. So first thing here, since this is a bit more complicated, I need a stronger version, not just what I said here, this Van Kampen Flores. I need something called homological Van Kampen Flores, because here we go to homology somehow. So I will explain what this homological embedding is on the next slide. And here I just want to mention that this was everything under the assumption that the homological complexity is trivial, that everything can be filled. And you saw that in the theorem we allowed like more path connected components and things like that. We allowed some holes. So to deal with them, we need to use some additional Ramsey type stuff, which will make the bounds like pretty large. but it's like possible to do these things. Okay. So this is what is the homological Z2 embedding. So if you know a bit of topology, this is the precise definition. If you don't worry, don't read it, and I will explain it on those three pictures. Yeah. So this is the standard embedding of K4 we all know, yeah, like embedding. If you played with graphs, you know what is a weak Z2 embedding. This is like topological drawings of graphs. This is that the edges they can cross. We don't care what happened for adjacent edges. They can cross as well, like here, red and blue or red and violet. But what we care about is that independent edges, meaning like disjoint edges, they can cross only even a number of times. Yeah. And if you have, so this is called weak Z2 embedding, and I think Hanane-Tat theorem in the plane tells you that those two things are basically the same. Yeah, that if you can something embed in this weird sense, you can also embed it in a standard way.
Isn't the blue and the green cross once?
Yeah, but they are adjacent. They are adjacent, so I don't.
Okay.
I don't care. Okay, and homological Z2 embedding is something even worse. So here, what we allow is that not only that the vertex is mapped to a vertex, but now vertex can be mapped to an odd number of vertices. So here, this top vertex now is mapped to 3 vertices. Yeah. And what I will count is intersections of images of independent edges. So now what happens that this blue edge is now mapped to these 3 blue edges. And if I want to count this blue and say this orange, so it has to be even. And what is also hidden here is that it might look like that this is really random, but it's not that much. It must respect boundaries. So if it was, so here a boundary was, what is boundary of edge? Just the 2 vertices. So here, if I look at the boundary of the image, it must be that this here is like once, I mean, odd number of times, and here any of those images is also like odd number of times. And I count in Z2. So here I see the violet edge is once. Here I have 3 times, here I have once, so it's like fine. So it's such kind of strange thing. Here this black thing, it has no boundary, so this is also fine. So it's allowed in this homology. And when we were proving this Helly thing, like that bounded homological complexity implies bounded Helly, we show that there is no homological Z2 embedding of the half skeleton of D plus 2 dimensional simplex. And so even if you allow this crazy type of embeddings, you will not succeed with the half skeleton of D plus 2 simplex. Okay. So this is what I wanted to say about this homological embeddability, not embeddability. And let's go back to our picture. So this is what we know. We have constant constant homological complexity implies Radon, and now we get a fractional Helly of large order. Here it's like very large because the Ramsey arguments, which I didn't tell you, they produce huge bounds. Okay, so now if you have this, you can ask 2 questions. First one is, what about here, about the constantness? So what if it will not be, so can I get something similar if this is not constant? Well, this falls under an umbrella of long-term project of Gilcalai and Roy Meshulam regarding homological VC dimension. And one of their conjecture is that if now I measure or count the sum of the Betty numbers, not the maximum as V, but if the sum is polynomial in the size of the subfamily, so they conjecture then we have a fractional Helly of order D. Yeah, so this is hopelessly open. And what we were able to show with Xavier, Goaok, Andreas Holmsen is basically that here, if we don't bound it by a polynomial, but just by a constant, then we can indeed get a fractional Helly of order D. So basically, from the previous slide, here is that here I get fractional Helly of small order. We could reduce this large order to a small one. Here is just to recall what is the fractional Helly. So if positive fraction of D plus 1 tuple intersect, then I have a point contained in a positive fraction of all points. Oh, sorry, positive. Okay, fraction of all sets. Yeah, and so here is our theorem again. So we show that if I have a family with bounded homological complexity, I know it has a fractional Helly property of order D. Here is a sketch of the proof. The assumptions are at the bottom. Here I have a family with bounded homological complexity. This is an assumption of the fractional Helly, positive fraction of D plus 1 tuples intersect. Here is a conclusion. There is a point contained in a positive fraction of all the sets. Sketch of the proof. What is on the left? Here we have seen, this is what I explained, that if we have bounded homological complexity, we have bounded Radon. Result on Holmsen and Lee says us that we have a fractional Helly of very large order. Yeah, so I will not discuss. So we have this part here, and I will not discuss it more. Instead, I want to focus on the right-hand side. And this is if I have this family with bounded homological complexity, I know that positive fraction of D plus 1 tuples intersect. I will show that that's smaller, but still positive fraction of D plus 2 tuples intersect, then D plus 3 tuples, and so on, and so on, and so on, until I hit the bound here I have. Yeah? And this is called, we call it stepping up process. And I want to mention here that this stepping up is successful only when we have the upper bound here, when we have a stopping point. Yeah, so it might look on the first sight that this result just improves my previous result. This is true, but the previous result is necessary for that. Without that, we would not, this would not say as much. Yeah, we really need the stopping point here, which we have from this. So it's like very nice in some sense, that if you prove some bound, then you can reduce it. Okay. Now, I want to explain you this stepping up a bit more. And so what we have here. So I have family of sets, bounded homological complexity. I fix some K, and I want to show that if positive fraction of K tuples intersect, also positive fraction of K plus 1 tuples intersect. So computatorics behind is that I consider a hypergraph where vertices will correspond to sets in my family and edges will now correspond to intersecting K tuples. Yeah, so each intersecting K tuples gives me a hyperedge. Now here the assumption that positive fraction of K tuples intersect tells me that my hypergraph has very many edges. Yeah, has positive fraction of hyperedges. Now, a result by Erdesh and Shimonovich from extremal combinatorics tell us that under this assumption, if n is fixed, there is a positive fraction for nx, positive fraction of all k-partite, k-uniform hypergraphs are contained in my given hypergraph. So this K, K, N, 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 N is this creature here. Yeah, so I have K partite, K uniform hypergraph, and here this is size N, this is of size N, this is of size N. And K part of the proof is that for each such creature in my hypergraph, we find an intersecting K plus 1 tuple of this bounded size. And this gives us the result because I have, if positive fraction of K tuples intersect, I have positive fraction of these creatures, and each such creature gives me an intersecting K plus 1 tuple. And now by simple double counting, I just guarantee that I get distinct intersecting K plus 1 tuples, or like I get enough of distinct intersecting K plus 1 tuples, and this is what I wanted to show here. Yeah. So this is the K part here, what we need to show. Yeah. And okay, so I would say that a very important observation was the following one, and it was that we can represent these creatures by grids. Yeah. How? So for example, if I here take a like triangle or like edge, which corresponds to third point from this partitive part, first from that, and second from that, this gives me a point with coordinates 3, 1, and 2. Yeah. Once again, this was a third point from this first partitive. This was a first point from the second. This was a second point from the third. And this gives, this gives me a coordinates on my point in a grid. So now before we worked with simplicial complexes or something, and now we will work with cube complexes. Yeah. And in order to use some results known for simplicial complexes, like what we used before, this embeddability stuff, when I told you that this skeleton of right dimension does not embed. So I could prove the same for like cubical complexes, but instead of that, like proving everything separately, I just embed simplicial complex in a very nice way here, and use the results which I know holds for simplicial complexes also here in the grid. And the embedding is done via something called star convexity, which is a very nice tool introduced by Boris Buk, Gabriel Niváš, and Jirka Matoušek. Basically, this what is here is a triangle. It has 3 vertices. Those are the edges, the boundary, and this is the interior. So basically we map the points on the main diagonal and then do these things. And somehow this is consistent and everything will work like this. Okay. And for the Ramsey arguments we have, I want to show you one nice thing which we need. It might look like a technical result, but I like the proof, so I decided that I want to share it with you. So what is the setting? I have a small grid on the left. This is a grid 3 times 3. And I have a large grid on the right. This is a grid 8 times 8. And what happens here is that the edges of the big grid are labeled by 0 or 1. So this is what I have here. And what I'm looking for is if I can find a copy of this small grid inside the big one. So this is the blue one. This is a copy of that one. It's just scaled, but that's fine. And the rule here is that if I look on the image of an edge here, so image of this edge is sum of those 2 edges. And what I want is that when I sum the numbers here, I get 0 for every edge. Also here I have it 1 plus 1, this is 0 modulo 2. 1 plus 0 plus 1, again, here I have only 0, so this is fine, and so on. And the claim is that I can always do it. Yeah, those meaning that if I have a small grid, so what are the parameters here? Yeah, if I have a small grid, so then I find a big grid such that no matter which labeling here I choose, I will always find a copy I will always find a copy of this small grid with my properties, favorable properties. And it also holds more generally that I don't need to label only edges, but I can label also faces of either dimensions. Here, for example, I can label the squares. And this is what I would like to show you how to prove it when I label the squares in the plane. So I have one such labeling. And what I will do, I will form another labeling. Now I will assign a label to the vertices in the following way. I take a vertex and I look on the rectangle where I have this vertex and the bottom left. Yeah. So I form this rectangle and the label here is sum of the labels inside. So here it was 1 and 1. So 1 plus 1 is 0 modulo 2. So I put 0 to this vertex. So for example, for this vertex, I just sum all these 1, 0, 1, 0, 1, 0, 1. So this was odd number of ones. So here the result is 1. And now here is the magic. If I find a monochromatic, so what I claim, monochromatic grid here gives me exactly what I wanted. Why? So how do I count what is here, for example, sum of those two, or say sum of those four? How do I count it? So inclusion exclusion tells me that the area of the blue part here is A, this is area of the big thing, minus B, which is this area, minus C, and I need to add D because I subtracted twice. Yeah? So it's A minus B minus C plus D. But now if all these things have the same color, it's the same number, I get 0. Yeah, and this is exactly what I wanted. This is exactly what means that if I sum the things here for any of those like small parts, I get 0. So I reduce it to fact that I need to find a monochromatic copy, and this can be proved either easily by induction, or it's a direct consequence of something called Galaiwit theorem, which tells you exactly this, that you can find, so if you have a finite set, some number, and another finite set called by k-colors, you can, and this bigger thing contains a monochromatic homothetic copy of the smaller one. Yeah. Maybe it was not very precise what I just said, but I'm just telling you this is like either you can prove it directly or it's a well-known trick, a well-known theorem related to Helly. It's called convex.
It's a nice problem and a nice solution. Very nice.
Thanks. Yeah, and that's basically almost everything I wanted to tell you. So here is a concluding or slide with concluding remarks. So this is basically the result we have. Bounded, so homological complexity bounded by a constant, give us a fractional Helly property of order B. Now, you may ask, is it necessary to bound really all first d half Betti numbers? The answer is yes, it is. So so we have an example when all Betti numbers are 0 but 1, which can be infinite, like large enough, infinite, then the theorem doesn't hold. And doesn't hold for fractional Helly, doesn't hold for Radon, doesn't work for Helly. Yeah. So there is basically one example you can cook up, or like you can adapt to work for all the cases. So this is really necessary. And second thing you can ask, well, because what I show you, almost all the steps were not dependent on the fact that we work in d-dimensional space. I mean, in Euclidean d-dimensional space. And the only part where it was needed was the homological non-embeddability. All the other things, they were combinatorial or like other, and they were independent on the space. So now the basic question, or like very annoying question, is if we have a homological von Kampen-Flores for embeddings into manifolds. Because if yes, then all the results I have shown you will work as well on manifolds, like fractional Helly, PQ, Perberg, all these things we would have immediately. And there is some hope, because we know that on surfaces, homological von Kampen-Flores is basically the same as standard von Kampen. So we have the results for surfaces, but we don't know for for other manifolds, or like for high dimensions. Who knows? And another basic question is the one of Gil and Roy about what happens here if we allow the Betti numbers, the sum of the Betti numbers grows polynomially in the size of the sets of the subfamily which we intersect. This is a second very annoying question in this area. Yeah, and this is everything I wanted to tell you.